Astronautics is the science and technology of space travel and exploration. It encompasses a wide range of disciplines, including physics, engineering, mathematics, and computer science. Let's break down the key aspects of astronautics. 1. Definition and scope. Astronautics, derived from the Greek words astron, star, and nauts, sailor. Astronautics literally means sailing among the stars. It involves the design, development, and operation of spacecraft and the study of the physical and technological principles that enable space travel. 2. Key disciplines. A. Rocketry and propulsion. Rocketry, the science of designing and building rockets, which are vehicles that propel themselves by expelling exhaust gases at high speed. Propulsion systems, these include chemical rockets, solid, liquid, and hybrid, ion thrusters, and nuclear propulsion. Each system has its own advantages and applications depending on the mission requirements. B. Orbital mechanics. Celestial mechanics, the study of the motions of celestial bodies under the influence of gravitational forces. Orbital dynamics, understanding how spacecraft move in space, including the calculation of orbits, trajectories, and maneuvers needed to reach and navigate within space. C. Spacecraft design. Structural engineering, designing the physical structure of spacecraft to withstand the harsh conditions of space, including extreme temperatures, vacuum, and radiation. Systems engineering, integrating various subsystems, for example, power, communication, life support, to ensure the spacecraft functions as a cohesive unit. D. Guidance, navigation, and control. GNC guidance, determining the desired path for the spacecraft to follow. Navigation, determining the spacecraft's current position and velocity. Control, adjusting the spacecraft's orientation and trajectory to follow the desired path. 3. Historical development. A. Early theories and experiments. Konstantin Tsiolkovsky developed the rocket equation and proposed the use of rockets for space travel. Robert H. Goddard launched the first liquid-fueled rocket, demonstrating the feasibility of controlled rocket flight. B. The space race. Sputnik 1, the first artificial satellite, launched by the Soviet Union in 1957, marking the beginning of the space age. Apollo program, NASA's program that landed humans on the moon, showcasing the pinnacle of human space exploration. 4. Modern applications. A. Satellite technology. Communication satellites enable global telecommunications, broadcasting, and internet services. Earth observation satellites monitor environmental changes, weather patterns, and natural disasters. B. Human spaceflight. International Space Station, ISS, a collaborative effort for scientific research and international cooperation in space. Commercial spaceflight. Companies like SpaceX and Blue Origin are developing technologies for space tourism and interplanetary travel. C. Deep space exploration. Mars rovers, robotic missions exploring the Martian surface to search for signs of past life and prepare for human missions. Interstellar probes, missions like Voyager 1 and 2, which have traveled beyond our solar system to study the outer planets and interstellar space. 5. Future prospects. A. Lunar and Martian colonization. Artemis program, NASA's initiative to return humans to the moon and establish a sustainable presence. Mars missions, plans for human exploration and potential colonization of Mars. B. Advanced propulsion technologies. Ion thrusters provide efficient propulsion for long-duration missions. Nuclear thermal propulsion offers higher thrust and efficiency for deep space exploration. 6. Challenges and considerations. A. Space environment, radiation, protecting astronauts and electronics from harmful cosmic radiation. Microgravity, understanding the effects of prolonged weightlessness on the human body and developing countermeasures. B. Sustainability, space debris, managing and mitigating the growing problem of space junk to ensure safe operations in orbit. Resource utilization, developing technologies for in situ resource utilization, IRU, to support long-term missions. Astronautics is a multidisciplinary field that continues to evolve, driven by human curiosity and the desire to explore the unknown. It combines theoretical knowledge with practical engineering to push the boundaries of what is possible in space exploration. Human spaceflight presents a unique set of challenges that span various domains, from engineering and biology to psychology and logistics. Here are some of the key challenges. 1. Radiation exposure. Space radiation. Space is filled with high-energy particles from the sun, solar radiation, and from outside our solar system, cosmic rays. These particles can damage cells and increase the risk of cancer and other health issues. Protection. Developing effective shielding materials and strategies to protect astronauts from radiation is crucial. This includes spacecraft design, habitat construction, and possibly even pharmaceutical countermeasures. 2. Microgravity effects. Physical health, muscle atrophy and bone density loss. In microgravity, muscles and bones weaken because they are not used as much as on Earth. Astronauts must exercise regularly to mitigate these effects. Fluid redistribution. Fluids in the body shift towards the head in microgravity, which can cause vision problems and increased intracranial pressure. Long-term solutions. Research is ongoing to develop better exercise equipment and routines, nutritional supplements, and potential pharmaceutical treatments to counteract these effects. 3. Psychological and social challenges. Isolation and confinement. Long-duration missions, such as those to Mars, involve extended periods of isolation and confinement, which can lead to psychological stress, depression, and interpersonal conflicts. Countermeasures. Strategies include careful crew selection and training, providing mental health support, and ensuring effective communication with Earth. 4. Life support systems. Sustainability. Air and water recycling. Spacecraft must have systems to recycle air and water to support life for extended periods. This includes removing carbon dioxide, generating oxygen, and purifying water. Food supply. Providing a sustainable and nutritious food supply is essential. This involves developing methods for growing food in space and ensuring long-term storage of food supplies. 5. Spacecraft design and reliability. Engineering challenges. Durability. Spacecraft must be designed to withstand the harsh conditions of space, including extreme temperatures, vacuum, and micrometeoroid impacts. Redundancy and reliability. Systems must be highly reliable, with redundant components to ensure that critical functions can continue even if some parts fail. 6. Mission planning and logistics. Complexity. Trajectory and navigation. Planning precise trajectories and navigation for long-duration missions is complex and requires advanced computational tools and constant monitoring. Supply chain management. Ensuring that all necessary supplies and equipment are available and can be delivered to the spacecraft or habitat as needed. 7. Health monitoring and medical care. Medical challenges. Health monitoring. Continuous monitoring of astronauts' health is essential to detect and address any issues early. Medical care. Providing medical care in space is challenging due to limited resources and the need for remote diagnosis and treatment. Telemedicine and portable medical devices are critical components. 8. Re-entry and landing. Safety. Heat shielding. Spacecraft must be equipped with heat shields to protect against the intense heat generated during re-entry into Earth's atmosphere. Landing precision. Ensuring a safe and precise landing is crucial, especially for missions returning from other planets. 9. Ethical and legal considerations. Ethics. Human rights. Ensuring the rights and well-being of astronauts are protected during missions. Planetary protection. Preventing contamination of other planets with Earth life and vice versa. Legal framework. Space law. Developing and adhering to international laws and agreements governing space exploration and the use of space resources. 10. Technological innovation. Continuous improvement, advancements, ongoing research and development are necessary to improve existing technologies and develop new ones to address the challenges of human spaceflight. Collaboration, international cooperation and collaboration with private industry are essential to share knowledge, resources, and expertise. Human spaceflight is a complex and multifaceted endeavor that requires addressing a wide range of challenges. Each of these challenges presents opportunities for innovation and advancement, driving the progress of space exploration. Life support systems in space are crucial for maintaining a habitable environment for astronauts. These systems ensure that the basic needs for survival, such as breathable air, clean water, and a stable temperature, are met. Let's explore the key components and challenges of life support systems in space. 1. Air revitalization. Oxygen generation, electrolysis of water. This process splits water into oxygen and hydrogen using electricity. The oxygen is used for breathing, while the hydrogen can be vented into space or used in other processes. Chemical oxygen generators. These devices produce oxygen through chemical reactions, often used as backups. Carbon dioxide removal, CO2 scrubbers. These devices remove carbon dioxide from the cabin air. The International Space Station, ISS, uses systems like the Carbon Dioxide Removal Assembly, CDRA, and the Sabatier system, which converts CO2 into water and methane. Trace contaminant control, filters and catalytic converters. These systems remove harmful trace gases and particulates from the air, ensuring it remains safe to breathe. 2. Water recovery and management. Water recycling, urine processor assembly, UPA. This system recycles urine into potable water. It involves distillation and filtration processes to ensure the water meets stringent purity standards. 2. Water Recovery System (WRS). This system recycles water from various sources, including cabin humidity and hygiene activities, to provide clean water for drinking, food preparation, and other uses. 3. Temperature and humidity control. Thermal control systems. Active thermal control uses pumps and heat exchangers to regulate temperature. Heat generated by electronic equipment and human bodies is transferred to radiators and dissipated into space. Passive thermal control involves insulation and reflective coatings to maintain stable temperatures. Humidity control, condensate removal. Excess moisture in the air is condensed and removed to prevent mold growth and equipment damage. The recovered water is often recycled. 4. Waste management. Solid waste, compaction and storage. Solid waste is compacted and stored until it can be disposed of, either by returning it to Earth or burning it up in the atmosphere during re-entry. Liquid waste, urine processing. As mentioned, urine is processed and recycled into potable water. Other liquid wastes are managed similarly to ensure minimal resource loss. 5. Food supply and nutrition. Food storage. Shelf-stable foods. Foods are specially processed and packaged to have a long shelf life without refrigeration. This includes freeze-dried and thermostabilized meals. Nutritional balance, diet planning. Astronauts' diets are carefully planned to ensure they receive all necessary nutrients. This includes vitamins and minerals that might be lacking in space food. 6. Health monitoring and medical care. Health monitoring. Biometric sensors. Wearable sensors monitor astronauts' vital signs, such as heart rate, blood pressure, and oxygen levels. Regular checkups. Astronauts undergo regular health assessments to detect and address any medical issues early. Medical equipment. Telemedicine enables remote diagnosis and consultation with medical experts on Earth. Portable medical devices. Compact and multifunctional devices are used to provide medical care in space. 7. Challenges and innovations. Radiation protection. Shielding materials. Developing materials that can effectively block or reduce radiation exposure is a major focus. This includes using water, polyethylene, and other materials as shields. Resource efficiency. Closed-loop systems. Maximizing the recycling and reuse of resources is essential for long-duration missions. Innovations in closed-loop life support systems aim to minimize the need for resupply from Earth. Psychological support. Mental health. Providing psychological support and maintaining crew morale are critical, especially on long missions. This includes regular communication with family and friends, recreational activities, and mental health resources. Life support systems are a testament to human ingenuity and the ability to create sustainable living conditions in the harsh environment of space. Continuous research and development are essential to improve these systems and support future missions to the Moon, Mars, and beyond. Long-duration space missions, such as those to Mars or extended stays on the International Space Station, ISS, present a variety of challenges that must be addressed to ensure the safety and well-being of astronauts. Here are some of the key challenges. 1. Radiation exposure. Space radiation, cosmic rays and solar radiation. Outside Earth's protective magnetic field, astronauts are exposed to higher levels of cosmic rays and solar radiation. This increases the risk of cancer, cataracts, and other health issues. 1. Protection strategies. Developing effective shielding materials and strategies, such as using water or polyethylene, is crucial to protect astronauts from harmful radiation. 2. Microgravity effects. Physical health, muscle atrophy and bone density loss. In microgravity, muscles and bones weaken due to lack of use. Astronauts must engage in regular exercise to mitigate these effects. 1. Fluid redistribution. Fluids in the body shift towards the head, which can cause vision problems and increased intracranial pressure. This condition is known as spaceflight-associated neuroocular syndrome (SAN). 1. 3. Psychological and social challenges. Mental health, isolation and confinement. Long missions involve extended periods of isolation and confinement, which can lead to psychological stress, depression, and interpersonal conflicts. 2. Countermeasures. Strategies include careful crew selection and training, providing mental health support, and ensuring effective communication with Earth. 4. Life support systems. Sustainability, air and water recycling. Spacecraft must have systems to recycle air and water to support life for extended periods. This includes removing carbon dioxide, generating oxygen, and purifying water. 3. Food supply. Providing a sustainable and nutritious food supply is essential. This involves developing methods for growing food in space and ensuring long-term storage of food supplies. 5. Spacecraft design and reliability. Engineering challenges, durability. Spacecraft must be designed to withstand the harsh conditions of space, including extreme temperatures, vacuum, and micrometeoroid impacts. 3. Redundancy and reliability. Systems must be highly reliable, with redundant components to ensure that critical functions can continue even if some parts fail. 6. Health monitoring and medical care. Medical challenges, health monitoring. Continuous monitoring of astronauts' health is essential to detect and address any issues early. 1. Medical care. Providing medical care in space is challenging due to limited resources and the need for remote diagnosis and treatment. Telemedicine and portable medical devices are critical components. 7. Re-entry and landing. Safety, heat shielding. Spacecraft must be equipped with heat shields to protect against the intense heat generated during re-entry into Earth's atmosphere. 3. Landing precision. Ensuring a safe and precise landing is crucial, especially for missions returning from other planets. 8. Ethical and legal considerations. Ethics, human rights. Ensuring the rights and well-being of astronauts are protected during missions. Planetary protection. Preventing contamination of other planets with Earth life and vice versa. Legal framework. Space law. Developing and adhering to international laws and agreements governing space exploration and the use of space resources. 9. Technological innovation. Continuous improvement, advancements, ongoing research and development are necessary to improve existing technologies and develop new ones to address the challenges of human spaceflight. 3. Collaboration, international cooperation and collaboration with private industry are essential to share knowledge, resources, and expertise. Addressing these challenges requires a multidisciplinary approach, combining advances in engineering, biology, psychology, and international cooperation. Each challenge presents opportunities for innovation and progress in the field of space exploration. The operation of a space rocket involves a complex interplay of physics, engineering, and technology. Let's break down the key components and processes involved in getting a rocket from the ground into space. 1. Rocket structure. A. Stages. Multistage rockets. Rockets are often divided into multiple stages, each with its own engines and fuel. As each stage completes its burn, it is jettisoned to reduce weight, allowing the remaining stages to accelerate more efficiently. This staging process is crucial for reaching the high velocities needed to escape Earth's gravity. 1. B. Components. Payload. The part of the rocket that carries the mission's cargo, such as satellites, scientific instruments, or crew modules. Propellant tanks store the fuel and oxidizer needed for combustion. Engines provide the thrust needed to propel the rocket. 2. Propulsion systems. A. Thrust generation. Newton's third law. Rockets operate on the principle of action and reaction. When fuel combusts in the engine, it produces high-speed exhaust gases that are expelled out of the nozzle, generating thrust in the opposite direction. 2. B. Types of propulsion. Chemical rockets use liquid or solid propellants. Liquid rockets mix fuel and oxidizer in a combustion chamber, while solid rockets have propellant that is pre-mixed and solidified. Ion thrusters use electric fields to accelerate ions, providing efficient but low-thrust propulsion suitable for long-duration missions. 3. Launch sequence. 8. Pre-launch preparations. Fueling. The rocket is fueled with propellants, and all systems are checked for readiness. Countdown. A precise countdown sequence ensures all systems are synchronized for launch. B. Liftoff. Ignition. The engines ignite, producing thrust that overcomes Earth's gravity. Ascent. The rocket ascends through the atmosphere, with each stage burning its fuel and then being jettisoned. 4. Guidance, navigation, and control. GNC. 8. Guidance, trajectory planning. The desired path of the rocket is calculated to ensure it reaches its intended orbit or destination. B. Navigation, position and velocity tracking. Sensors and onboard computers continuously monitor the rocket's position and velocity to ensure it stays on course. C. Control, thrust vectoring, adjusting the direction of the engine nozzles to steer the rocket. Reaction control systems, RCS, small thrusters that provide fine adjustments to the rocket's orientation and trajectory. 5. Orbital insertion. At achieving orbit velocity requirements. To achieve a stable orbit, the rocket must reach a specific velocity and altitude. For low Earth orbit, LEO, this is approximately 7.8 km /s, 17,500 miles per hour. Circularization. After reaching the desired altitude, the rocket performs a burn to circularize its orbit, ensuring it remains stable. 6. Payload deployment. 8. Separation, payload release. Once in the correct orbit, the payload is separated from the rocket. This can involve deploying satellites, releasing scientific instruments, or positioning crew modules for docking with space stations. B. Post-deployment operations, payload activation. The payload systems are activated, and it begins its mission, whether it's communication, observation, or scientific research. 7. Re-entry and recovery, if applicable. 8. Re-entry, heat shielding. For missions returning to Earth, the spacecraft must be protected from the intense heat generated during re-entry. Heat shields absorb and dissipate this heat. Controlled descent, the spacecraft's descent is controlled to ensure a safe landing. B. Recovery, landing, the spacecraft lands either on land or in the ocean, where recovery teams retrieve it and any scientific data or samples it carries. 8. Challenges and innovations. 8. Engineering challenges, structural integrity, rockets must withstand extreme forces during launch and ascent. Thermal management, managing the heat generated by engines and during re-entry. B. Technological innovations, reusable rockets, companies like SpaceX are developing rockets that can be reused, significantly reducing the cost of space travel. Advanced propulsion, research into new propulsion methods, such as nuclear thermal propulsion, aims to make space travel more efficient and faster. The operation of a space rocket is a testament to human ingenuity and the application of fundamental scientific principles. Each component and process is meticulously designed and tested to ensure the success of the mission. Reusable rockets are a significant advancement in space technology, aimed at reducing the cost of space travel and increasing the frequency of launches. Let's explore the key aspects of reusable rockets in detail. 1. Concept and benefits. 8. Definition, reusable rockets, these are rockets designed to be recovered and flown multiple times. Unlike traditional expendable rockets, which are discarded after a single use, reusable rockets can be refurbished and relaunched. B. Benefits, cost reduction, reusing rockets significantly lowers the cost of space missions by reducing the need to build new rockets for each launch. 1. Increased launch frequency, the ability to quickly refurbish and relaunch rockets allows for more frequent missions, supporting a variety of commercial, scientific, and exploratory activities. 1. 2. Key technologies and components. A. Landing systems, vertical landing, rockets like SpaceX's Falcon 9 use controlled vertical landings to return to Earth. This involves reigniting the engines to slow the descent and deploying landing legs for a stable touchdown. 2. Grid fins, these are aerodynamic control surfaces used during re-entry to steer the rocket and ensure a precise landing. 2. B. Heat shields, thermal protection, reusable rockets are equipped with heat shields to protect them from the intense heat generated during re-entry into Earth's atmosphere. 1. C. Refurbishment, inspection and repair, after landing, rockets undergo thorough inspections and necessary repairs to ensure they are ready for the next flight. This process includes checking the engines, avionics, and structural components. 1. 3. Notable examples. A. SpaceX Falcon 9, first reusable orbital class rocket. Falcon 9 is designed to transport payloads to Earth orbit and beyond. Its first stage is capable of landing and being reused multiple times. 2. Milestones. In 2017, SpaceX made history by successfully launching and landing a previously used Falcon 9 rocket booster. 3. B. Blue Origin New Shepard, suborbital flights. New Shepard is designed for suborbital space tourism and scientific research. It features a reusable booster that lands vertically after each flight. 1. C. SpaceX Starship, fully reusable system. Starship aims to be a fully reusable spacecraft capable of carrying large payloads and passengers to destinations like the Moon and Mars. It consists of a reusable booster, Super Heavy, and a spacecraft, Starship, that can both be recovered and reused. 1. 4. Challenges and innovations. 8. Engineering challenges, durability, reusable rockets must be built to withstand multiple launches and re-entries, which requires robust materials and design. Precision landing, achieving precise landings is critical for recovery and reuse. This involves advanced guidance and control systems. 2. B. Innovations, autonomous landing platforms. SpaceX uses autonomous drone ships as landing platforms for rockets returning from high-velocity missions. These ships are stationed in the ocean and provide a stable landing surface. 2. Rapid turnaround, efforts are being made to reduce the time required for refurbishment, aiming for rapid turnaround times between launches. 1. 5. Future prospects. At increased accessibility, lower costs, continued advancements in reusable rocket technology are expected to further reduce launch costs, making space more accessible for a wider range of missions and organizations. 1. B. Interplanetary missions, Mars and beyond. Reusable rockets are a key component of plans for interplanetary missions, including human exploration of Mars. The ability to reuse spacecraft will be crucial for the sustainability of long-duration missions. 1. Reusable rockets represent a transformative shift in space exploration, enabling more frequent and cost-effective access to space. As technology continues to advance, the potential for reusable rockets to support ambitious missions and commercial ventures will only grow. Reusable rockets face significant challenges when re-entering Earth's atmosphere due to the extreme heat generated by friction with air molecules. Here's a detailed look at how they handle this heat. 1. Thermal Protection Systems (TPS). A. Heat shields. Ablative heat shields. These shields absorb heat by gradually charring, melting, and vaporizing. This process dissipates heat away from the rocket. Early space missions, like Apollo, used ablative heat shields. 1. Refractory heat shields, made from materials like reinforced carbon-carbon (RCC) and ceramics. These shields can withstand high temperatures without ablating. They are used in modern reusable rockets. 2. B. Insulation. Flexible insulation blankets. These are used to cover parts of the rocket that don't experience the highest temperatures. They provide thermal protection by reflecting and absorbing heat. 2. Aerodynamic design. A. Blunt body shape. Shockwave creation. A blunt body design creates a shockwave in front of the rocket during re-entry. This shockwave helps to keep some of the heat away from the rocket's surface, reducing the thermal load. 3. B. Grid fins and control surfaces. Stability and control. Grid fins and other aerodynamic surfaces help stabilize and control the rocket during re-entry. They also help manage the heat distribution across the rocket's surface. 4. 3. Engine reignition. At controlled descent, retropropulsion. Rockets like SpaceX's Falcon 9 use retropropulsion, where the engines are reignited during descent to slow down the rocket. This reduces the heat generated by atmospheric friction. 4. Material innovations. A. Advanced composites. Durable materials. Modern reusable rockets use advanced composite materials that can withstand high temperatures and repeated thermal cycling. These materials include carbon composites and high-temperature alloys. 2. B. Metallic TPS. Combination of materials. Some designs use a combination of metallic and ceramic parts to take advantage of the strengths of both materials. Metals are easier to inspect and maintain, while ceramics handle higher temperatures. 2. 5. Testing and iteration. 8. Real-world testing. Continuous improvement. Companies like SpaceX conduct extensive real-world testing to refine their thermal protection systems. Each flight provides data that helps improve the durability and performance of the heat shields. 5. B. Simulation and modeling. Predictive analysis. Advanced simulations and modeling are used to predict the thermal loads and behavior of materials during re-entry. This helps in designing more effective TPS. 2. 6. Examples of reusable rockets. A. SpaceX Falcon 9. Heat shield and grid fins. Falcon 9 uses a combination of heat shields and grid fins to manage re-entry heat. The engines are also reignited to slow the descent. 4. B. Blue Origin New Shepard. Thermal protection. New Shepard uses a combination of heat-resistant materials and aerodynamic design to handle re-entry heat. 6. Reusable rockets represent a significant advancement in space technology, making space travel more cost-effective and sustainable. The continuous development of thermal protection systems and materials is crucial to their success. Heat shields are critical components in spacecraft, designed to protect them from the intense heat generated during re-entry into Earth's atmosphere. The materials used in heat shields must withstand extreme temperatures and provide effective thermal protection. Here are some of the key materials used in heat shields. 1. Ablative materials. A. Function, heat absorption and dispersion. Ablative materials absorb heat by undergoing controlled decomposition. As they heat up, they char, melt, and vaporize, carrying away heat and protecting the underlying structure. 1. B. Examples: phenolic impregnated carbon ablator. Pica used in NASA's Mars Science Laboratory and SpaceX's Dragon capsule. Pica is known for its high thermal resistance and ability to withstand extreme re-entry conditions. 1. UFcoat, used in the Apollo missions and the Orion spacecraft. UFcoat is a resin-based material that provides excellent thermal protection through ablation. 1. 2. Refractory ceramics. A. Function, high temperature resistance. Refractory ceramics can endure extremely high temperatures without melting or decomposing. They provide a stable thermal barrier during re-entry. 1. B. Examples: reinforced carbon-carbon, RCC used on the Space Shuttle's leading edges and nose cone. RCC is a composite material that can withstand temperatures up to 1,650 degrees Celsius, 3,000 degrees Fahrenheit. 1. Silica tiles. These lightweight tiles were used on the Space Shuttle's underside. They can withstand temperatures up to 1,260 degrees Celsius, 2,300 degrees Fahrenheit, and provide excellent insulation. 1. 3. Insulative foams. A. Function, thermal insulation. Insulative foams provide a lightweight and effective thermal barrier. They are often used in combination with other materials to enhance thermal protection. 1. B. Examples: flexible insulation blankets. These are used to cover parts of the spacecraft that do not experience the highest temperatures. They provide additional thermal protection and help manage heat distribution. 1. 4. Metallic heat shields. A. Function, durability and reflectivity. Metallic heat shields are designed to reflect and dissipate heat. They are often used in combination with other materials to enhance thermal protection. 2. B. Examples: aluminum and titanium alloys. These metals are used for their high strength-to-weight ratios and ability to withstand high temperatures. They are often used in structural components of heat shields. 2. 5. Composite materials. A. Function, combination of properties. Composite materials combine the benefits of different materials to provide enhanced thermal protection, durability, and weight savings. 3. B. Examples: ceramic matrix composites, CMC. These materials combine ceramic fibers with a ceramic matrix, providing high temperature resistance and structural integrity. 3. Carbon-carbon composites, used in high-temperature applications. These composites provide excellent thermal protection and structural strength. 3. 6. Innovations and future materials. A. Advanced coatings, thermal barrier coatings, TBCs. These coatings are applied to the surface of heat shields to enhance their thermal resistance and durability. They are often used in combination with other materials to provide multi-layered protection. 3. B. Nanomaterials, carbon nanotubes and aerogels. Research is ongoing into the use of nanomaterials for heat shields. These materials offer the potential for lightweight, highly effective thermal protection. 3. Heat shield materials are continuously evolving to meet the demands of modern space exploration. The development of new materials and technologies is crucial for ensuring the safety and success of future missions. Ceramic matrix composites, CMCs, are advanced materials that combine the high-temperature resistance of ceramics with the toughness and strength of fibers. They are designed to overcome the brittleness of traditional ceramics, making them suitable for high-stress, high-temperature applications. Let's delve into the key aspects of CMCs. 1. Composition and structure. A. Matrix material, ceramic matrix. The matrix is typically made from ceramic materials such as silicon carbide, SiC, alumina, Al2O3, or zirconia, ZrO2. The matrix provides the primary structural framework and high-temperature resistance. 1. B. Reinforcing fibers, ceramic fibers. These fibers are embedded within the ceramic matrix to enhance toughness and strength. Common fibers include silicon carbide fibers, carbon fibers, and alumina fibers. 1. C. Interface material, interface layer, a thin layer between the matrix and the fibers, often made from materials like carbon or boron nitride. This layer helps to deflect cracks and improve the composite's toughness. 2. Manufacturing processes. 8. Chemical vapor infiltration, CVI process, involves the infiltration of gaseous precursors into a porous preform, where they react to form the ceramic matrix. This method allows for precise control over the material properties. 2. B. Polymer infiltration and pyrolysis, PIP process. A polymer precursor is infiltrated into the fiber preform and then pyrolyzed, heated in the absence of oxygen, to convert it into a ceramic. This process is repeated to achieve the desired density and properties. 2. C. Melt infiltration, NI process, involves infiltrating a molten ceramic material into the fiber preform. This method is often used for producing silicon carbide-based CMCs. 2. 3. Properties and advantages. A. High temperature resistance, thermal stability. CMCs can withstand temperatures exceeding 1,500 degrees Celsius, 2,732 degrees Fahrenheit, making them ideal for high temperature applications such as turbine engines and aerospace components. 1. B. Toughness and strength, crack deflection. The fibers and interface layer help to deflect cracks, preventing catastrophic failure and enhancing the material's toughness. 1. C. Lightweight, density. CMCs are lighter than traditional metal alloys, which is advantageous for aerospace and automotive applications where weight reduction is critical. 1. 4. Applications. A. Aerospace, turbine blades and nozzles, used in jet engines and gas turbines due to their ability to withstand high temperatures and mechanical stresses. 1. Thermal protection systems, employed in spacecraft heat shields and re-entry vehicles to protect against extreme heat. 1. B. Automotive, brake discs. CMCs are used in high-performance brake systems for their excellent thermal conductivity and wear resistance. 1. C. Energy, nuclear reactors, utilized in components that require high temperature stability and radiation resistance. 1. 5. Challenges and future directions. A. Manufacturing costs, cost-effectiveness. The complex manufacturing processes and high material costs can make CMCs expensive. research is ongoing to develop more cost-effective production methods too. Beat material optimization, performance enhancement, continuous improvements in fiber and matrix materials, as well as interface design, are being pursued to enhance the performance and reliability of CMCs too. See broader applications, expansion, efforts are being made to expand the use of CMCs into other industries, such as biomedical implants and electronic devices, where their unique properties can offer significant advantages too. Ceramic matrix composites represent a significant advancement in materials science, offering a combination of high temperature resistance, toughness, and lightweight properties. Their development and application continue to evolve, driven by the demands of modern engineering and technology. The history of astronautics is a fascinating journey that spans centuries of theoretical groundwork, technological advancements, and human ingenuity. Let's delve into the key milestones and developments in this field. Early theoretical foundations. Isaac Newton, 1643 to 1727. Newton's work in the late 17th century laid the mathematical foundations for space travel. His laws of motion and universal gravitation, published in the Philosophiae Naturalis Principia Mathematica, 1687, provided the essential principles for understanding how objects move in space. 18th and 19th century mathematicians. Mathematicians like Leonhard Euler and Joseph Louis Lagrange made significant contributions to celestial mechanics, which is crucial for plotting the trajectories of spacecraft. Early visionaries and theoretical work. Konstantin Tsiolkovsky, 1857 to 1935. Often considered the father of astronautics, Tsiolkovsky developed the rocket equation, which describes the motion of vehicles that follow the principle of conservation of momentum. His work in the early 20th century laid the groundwork for modern rocketry. Robert H. Goddard, 1882 to 1945. An American physicist and engineer, Goddard is credited with creating and successfully launching the world's first liquid-fueled rocket in 1926. His innovations in rocket design were critical for future space exploration. The space race. World War II and V-2 rockets. During World War II, Germany developed the V-2 rocket, the world's first long-range guided ballistic missile. This technology was later adapted for space exploration. Sputnik and the beginning of the space race, 1957. The Soviet Union launched Sputnik 1, the first artificial satellite, on the 4th of October 1957. This event marked the beginning of the space race between the United States and the Soviet Union. 1. Yuri Gagarin and human spaceflight, 1961. On the 12th of April 1961, Soviet cosmonaut Yuri Gagarin became the first human to travel into space and orbit the Earth aboard Vostok 11. Apollo program and moon landing, 1969. The United States Apollo program achieved its pinnacle on the 20th of July 1969, when Apollo 11 astronauts Neil Armstrong and Buzz Aldrin became the first humans to land on the Moon. 1. This event was a significant victory for the US in the space race. Post-Apollo era and international cooperation. Space Shuttle Program, 1981 to 2011. NASA's Space Shuttle program enabled reusable spacecraft, which significantly reduced the cost of sending humans and cargo into space. The program facilitated numerous scientific missions and the construction of the International Space Station, ISS. International Space Station, 1998-present. The ISS is a collaborative project involving space agencies from the United States, NASA, Russia, Roscosmos, Europe, ESA, Japan, JAXA, and Canada, CSA. It serves as a microgravity laboratory for scientific research and international cooperation in space. Modern developments and private sector involvement. Mars exploration. NASA's Mars rovers, such as Curiosity and Perseverance, have been exploring the Martian surface, searching for signs of past life and preparing for future human missions. Private spaceflight. Companies like SpaceX, Blue Origin, and Virgin Galactic are pioneering commercial space travel. SpaceX's Falcon and Starship rockets aim to make space travel more affordable and accessible, with ambitious plans for missions to Mars. Future prospects. Artemis program. NASA's Artemis program aims to return humans to the Moon by 2024, with the goal of establishing a sustainable presence and preparing for future missions to Mars. Interplanetary travel. Advances in propulsion technology, such as ion thrusters and nuclear thermal propulsion, are being developed to enable faster and more efficient travel to distant planets and beyond. The history of astronautics is a testament to human curiosity and the relentless pursuit of knowledge. From the early theoretical work of Newton and Tsiolkovsky to the modern achievements of international space agencies and private companies, The journey into space continues to inspire and challenge us. That was all, goodbye.